Panjala from University of Kentucky, and it's entitled Hydrogen Production by Non-Oxidative Catalytic Decomposition of Methane.
Good morning, everybody. The topic of the presentation is hydrogen production by non-oxidative catalytic decomposition of methane. Traditionally, the hydrogen was produced by reforming of or partial oxidation of methane or higher hydrocarbons, and oxidative techniques also produces the hydrogen, but it contains CO as an impurity. CO is a poison for the platinum catalyst used in the fuel cells, PEM fuel cells. And CO removal need another additional process, that's a water gas shift or reverse methanation step. We want to produce a pure hydrogen by using non-oxidative techniques. Our approach is to use nanoscale alumina supported mono and binary metal catalysts to decompose methane at lower temperatures. Methane is very inert molecule. To decompose it, it needs higher energy. We are trying to lower the methane decomposition temperature. Here we have used undiluted methane as a feed, and catalyst should be able to withstand for carbon falling we are expecting. Catalyst, we have prepared metal solution added to the high surface area alumina water slurry and precipitated, washed with the deionized water, dewatered, extruded, vacuum dried. Before using the catalyst, we either oxidized or reduced or carburized in the presence of 20% methane in the hydrogen. The following experimental setup we have used for the generation of hydrogen from the methane. The catalyst was fixed bed reactor in a quartz reactor, and gases was fed with the mass flow meters, and all the product stream was analyzed by the online GC with the TCD. Here is some of the results of 5% iron and aluminum. Here the black ones, the black points, the curves, the methane, unreacted methane, and this is the hydrogen produced during the decomposition. This is the temperature profile and hydrogen formation and the reaction. They are like complementary to each other, and that's like mirror images. We are not seeing any other byproducts in this. Here is the 5% iron and aluminum, and we have taken the run with the non-catalytic, that's a thermal cracking. Methane cracking starts at above 900 degrees centigrade, whereas on the iron supported alumina catalyst, oxidized one starts at lower temperature, but it's not very active as compared to the reduced one, as compared to carburized one. In the overall, the carburized one was showing better activity. We stopped the reaction here because of the clogging up the reactor. It started developing the back pressure. We stopped the reaction here. Then the overall, the carburized catalyst shows better performance than any other catalyst on 5% iron and aluminum. Here we have used the moly and iron combined binary catalyst as well as mono moly iron catalyst. Here is the non-catalytic cracking, and here is the 0.5% moly and aluminum. This curve, the black one. And this one is 5% moly and aluminum. This one is 5% iron and aluminum. All this catalyst was pre-reduced as 1000 C. And coming to the binary metal, 0.5% moly and 4.5% iron and alumina shows better activity at lower temperatures. like as compared to the thermal cracking. The mass bar and exhaust spectroscopy indicates that iron moly catalyst having an alloy in a pre-reduced iron moly catalyst. Here is the another bimetallic catalyst. Here we have used palladium iron combinations. This is a thermal cracking curve, and this is the 5% iron on alumina. All this catalyst was pre-reduced at 700 C, whereas the 1000 C reduced iron catalyst was active. If you reduce at 700 C, it's not very active. And 0.5% palladium was still an active, but it deactivated at higher temperatures. Whereas in the overall, palladium and iron catalyst is very active. That's a bimetallic catalyst. It's very active, binary catalyst. And palladium exhaust indicates that there is a presence of palladium iron alloy phase in pre-reduced after reaction catalyst. Here is the nickel and iron based catalyst, binary as well as monometallic catalyst. Overall, this is the thermal cracking curve, and we have used a 5% nickel, 0.5% nickel, and binary catalyst. The binary catalyst shows a better activity. All this catalyst was pre-reduced as 1000 C. Here we stop the reaction because of the clogging of the reactor. Overall comparison of binary and monometallic catalyst pre-reduced at 700 C. In the overall, it shows a binary metal iron catalyst shows better activity than a monometallic iron catalyst pre-reduced at 700 C, and we could able to substantially decrease the decomposition temperature to around 400 to 500 degrees centigrade. Basically, methane non-oxidative decomposition, we produce methane decomposes into carbon and hydrogen. We are not producing any CO and CO2 in the reaction. That means we are producing pure product gas stream of hydrogen plus carbon. Carbon is a traditionally coke deposit flame for the fouling of the catalyst, and an oxidizer is used for the hinder the deposition of coke. But in our case, the opportunity is that whatever the carbon we are producing, it is in the form of multi-wall nanotubes. The potential applications of these nanotubes may be either hydrogen storage, electronic devices, or adsorbent. Here is a SEM image of multi-wall carbon nanotube grown over the moly iron bimetallic catalyst at 900 C. Here is another image of SEM picture of multi-wall carbon nanotubes grown over the nickel iron catalyst. Here is the carbon fiber grown over the palladium iron catalyst, as prepared palladium iron catalyst at 850 degrees centigrade. High resolution TM image shows the graphitic layers, and there is an iron particle in between the layers within the multi-wall nanotube. This is grown over the moly iron catalyst at 600 degrees centigrade. Multi-wall carbon nanotube and do not show any catalyst particle in our cases. Most of the tube ends do not show catalyst particle. As reported, like many multi-wall or single-wall tubes do show the catalyst particle at the two end. This is the another picture of the multi-wall nanotube on pre-reduced moly iron catalyst S900C. Coming to the conclusion, catalytic non-oxidated decomposition of methane produces pure hydrogen C. Absence of CO and CO2 in product stream eliminates subsequent purification steps. Catalyst reduces decomposition temperature by 400 to 500 degrees Celsius, can be regenerated by oxidation. Optimal reaction conditions, most of the carbon produce potentially useful multi-wall nanotube form. Thank you for your attention.
Any questions? Stephen?
Yeah, I got one question in reference to your temperature program reaction. When you showed the thermal reaction, the rate of that increase, I would guess, is proportional to the activation energy of the reaction. When you showed where you had a catalyst present, you moved the light off or where that began to a lower temperature, but that slope was pretty much the same. So I'm wondering, do you think you're getting that the role of that catalyst is initiating some free radical reactions? Is it still a free radical process, or do you think it's going on the surface?
I think so. It's a free radical mechanism.
Okay.
Yeah, decreasing the activation of methane. That's it.
Okay, but again, the slope is, they seem pretty
That's right.
parallel.
That's right.
Okay.
A quick question regarding your fibers and the multi-wall nanotubes. You showed a fiber later on in your talk, and I think the size scale, the diameter of the fiber was about 5 to 6 microns. But then before you showed multi-wall nanotubes, which probably had diameter of about 50 to maybe 70 nanometers. What are the structural differences between those two?
Depending upon the condition, you produce different kinds of nanotubes. If you go to the higher temperature, we could able to produce the nanofibers, graphitic layers. Like if you change the reaction condition, you can produce different sizes.
So the larger fibers, which have diameters in the order of microns, they basically have the same basic structure. They're multi-layered.
Yes, graphitic. But they're not tubes, some of them.
A couple of graphs you showed concentration of hydrogen decrease after 800 degrees, and why is that?
Well, maybe the catalyst may be centering, the metal may be going like growing the metal particle size on the catalyst. That may be the reason. I don't see any other reason. Whereas in the case of moly and iron one is not showing so much depth. In case of palladium and iron one showing as large depth.
And after that you showed that the concentration back up at the end. That's probably because of the thermal process.
Yeah, that's right. Thermal process may be overtaking the.
You indicated there's no metal particle, but you only showed one end of the tube.
Yeah, most of the
Is there a metal particle at the other end?
No, not at the end. It's in between the nanotubes, not on the end of the tube. We have not seen many metal particle in the nanotubes.
The catalyst stays behind on the surface,
And
and the tube grows from the surface.
Yes.
And so, traditionally, catalyst is carried over. Now,
Carried
its catalyst
over.
is not carried over, and so the other end has a metal particle, but it's on the surface of the catalyst.
Any more questions? Let's thank our speaker again.